And here we are, continuing through Chapter 7. We are now ready to begin Section 7.4, where we're going to learn trigonometric identities. Now, we know some trigonometric identities. We know things like the sine of negative theta is negative sine of theta. This is a trigonometric identity, an equation that relates different trigonometric functions against one another, basically. We also have like Pythagorean identities, sine squared theta plus cos squared theta equals 1. And we're going to really be playing around primarily with this one and get a whole bunch of new stuff. Okay. Pardon me. So, two functions are considered identically equal, and we usually just say equal, if any time they both exist, they are equal to one another. For example, you would say 3x is equal to 6x over 2. Any x for which they're both defined, the both sides will be equal to each other. Okay. So this is not, a hugely controversial. Two functions are equal if they are equal for every value of x that you can plug into them. Okay. And if you have one function equals another, you call this an identity. Okay. So here are some identities we already know. Tangent of theta is sine theta over cosine theta. Cotan theta is cosine over sine. Secant theta is 1 over cosine, etc. This is all familiar. Okay, we also have these Pythagorean and even odd identities. Anytime both sides exist, they're equal to one another. And again, we've worked with this. We know this. This is old hat. What we're going to be doing in this section is deriving new identities. Okay. Typically, what will happen is you're going to start with something and then manipulate it using existing techniques and make it look like something else. And the techniques you can use in an effort to change what something looks like is anytime you have something other than a sine or a cosine, replace it with sines and cosines and see if that simplifies things. We're also going to be doing a lot of multiplying by 1. For example, multiply something by sine theta over sine theta, and then that might help you cancel something out. We may sometimes combine fractions. We might write sums of ratios, sums of fractions as a single fraction. And conversely, you might do factoring, which is kind of like the opposite. Okay, these 4 little suggestions will become more clear as we start doing examples. So let's just start by simplifying tangent of theta over secant of by rewriting in terms of sines and cosines. So replace tangent with its corresponding parts and replace secant and see what you can do. Okay, so try that. Try to get this to look as simple as possible. Okay, so if we replace, and then, so let's just go through and do, sorry, since I did ask you to pause. So tangent of theta over secant of theta, we can replace tangent with sine theta over cosine theta and replace secant with 1 over cosine theta. And this might look worse because we have fractions over fractions. But what I can do is, so this is like the first thing that was in that list, replace everything with sines and cosines. Now let's multiply by 1. For example, I'm going to multiply by sine theta over cosine theta. That's just equal to 1, so I can multiply by it. But then what I can do is I can write the numerator and denominator as a single fraction. So I can call this sine theta cos theta over cos theta over cos theta over cos theta. So this denominator note is cosine theta over cosine theta. That's just going to be 1. And then here I have a cosine theta over cosine theta as well, so that's 1. So we get sine theta times 1 over 1, aka sine theta, which is a nice simplified expression. So what we've determined is that tangent of theta over secant of theta is equal to the sine of theta whenever both sides exist. So observe, there are values of theta for which the left-hand side, tangent theta over secant theta, doesn't exist. For example, pi over 2. Because the cosine of pi over 2 is 0, the secant of pi over 2 does not even exist. Okay, so I can't take the left-hand side, but I can take the sine of pi over 2. Similarly, yeah, that's it. Pi over 2 and 3 pi over 2, and its rotations around by periods. Okay, so we've determined a new trigonometric identity. Tangent theta over secant theta is always equal to sine of theta, provided both sides exist. Okay, so there's another example here, letter B. How would you show that sine of theta over 1 minus cosine is always equal to, at least as long as both sides are defined, 1 plus cosine theta over sine of theta? So you're given a very explicit suggestion. Multiply the numerator and denominator by 1 plus cosine of theta. So third example. Actually, let's just go ahead and do this one. So here's the bad way to do this. I want to be pretty clear about this. So a problem might say, for example, show this. Here's the problem. It could very well show up on a midterm. It's been a midterm before. Here's the bad way to do this. You write down sine theta over 1 minus cos theta equals 1 plus cos theta over sine theta, cross multiply to get sine squared theta equals 1 plus cos theta times 1 minus cos theta equals 1 minus cosine squared theta, and that's true. That is the Pythagorean identity. Sine squared theta is 1 minus cos squared theta. So this is true, so we started off with something true. Here's what's wrong with this. You are asked to show that this equality is true, meaning you don't actually know that it's true yet. That's exactly what you're trying to show is true. So if you start off by claiming, hey, this is true and I can write it down and I can work with it, well, if we already knew it was a legit thing to work with, why would you be asked to show that it's true? In other words, this approach of just writing down the problem and starting to manipulate it makes the mistake of assuming you're starting off with something correct when that's exactly what you need to demonstrate. Here's how you should do this problem. Whatever the sine of theta over 1 minus cosine theta is equal to, it's definitely equal to itself times 1. For example, times 1 plus cos theta over 1 plus cos theta. And here's the suggestion that was given. Multiply the numerator and denominator by 1 plus cos theta. All I'm doing is multiplying by 1, so this equal sign is totally justified. All I did was multiply by 1. Now, if I distribute that numerator, we get sine theta plus, actually, let's not distribute it. Let's just leave it as sine theta 1 plus cos theta. Now my denominator, I'm going to distribute the 1 minus cos theta times the 1 plus cos theta, and we end up 1 squared minus cos squared theta. And that was just doing some algebra. Okay, the numerator is just unaffected. The denominator, we just FOILed that out, and it's a difference of 2 squares factoring, so we have 1 minus cos squared theta, so that's fine. And then the Pythagorean identity we already know is true, so I'm not going to do anything to the numerator yet. But we know that 1 minus cos squared theta is sine squared theta. And that's just using the Pythagorean identity that we know is true. And now if I cancel a sine theta over sine theta, we get 1 plus cos theta over sine theta. So step by step, we did things that we already knew could work, and now we have justified that this is in fact equal to that. So don't do this problem by assuming it's true and manipulating it. You have to start with one side and do legitimate manipulations to it to transform it into the other side. Okay, so let's see what the third example here is. Simplify this thing by factoring. Okay, so we've got cos squared theta minus 1. I'm just writing the problem down. Tan theta cos theta plus tan theta. The suggestion is simplify by factoring, so I think, well, that numerator sure looks like a difference of 2 squares. Cos theta plus 1, cos theta minus 1. And the denominator, I can factor a tangent of theta out, leaving behind cos theta plus 1. And now I can cancel cos theta plus 1 over cos theta plus 1, leaving me just cos theta minus 1 over tangent of theta. It's not immediately clear if this is what the problem is asking us to stop at. Okay, so like part B, once we know these two sides were equal, we know we're done. It was a pretty clear objective. This just says simplify, and that's kind of squishy language. Is this simplified enough? I don't know. But the reason I say is because we can simplify this a little bit. So let's take that numerator and leave it alone for now. The denominator, I'm going to change to sine theta over cos theta. Then I'm going to multiply by 1, namely cos theta over cos theta. Because this denominator now simplifies down to just being sine theta, and the numerator is cos squared theta minus 1. So here's what we now have. Cos squared theta minus 1, sorry, cos squared theta minus cos theta when I distribute that cosine out. So here's what we have now. I'm erasing these intermediate steps. And not knowing in advance what simplify was asking, this line right here may very well have been the end of what was expected. We'll find out shortly when we actually see the book solution. But if you distribute that numerator out, it ends up being 10. There it is. We would end up with this. Cosine squared theta minus cosine theta over sine theta, which maybe that's considered simpler because it doesn't have a tangent in it. I don't know. So I tend to avoid using language simplify in an exam problem because when is simple enough is not necessarily clear. But we'll find out. Okay, we're about to see the suggested solutions to these. Whoops, I didn't realize there was a part D. Okay, so again, simplify. That's kind of vague, but can we take this and express it as a single fraction? What we're going to need to do is find a common denominator and then see what happens. And we don't have space to do it on this slide, so we'll wait for the official solution. Okay, so the first one said write them in terms of sines and cosines and see what simplifies down. Tangent is sine over cosine, secant is 1 over cosine. If you multiply by cosine over cosine or reciprocate the denominator either way, the cosines cancel out and you just end up with a sine theta. Okay, we already saw that. For part B, it said multiply numerator and denominator by 1 plus cos theta, so there's that. And again, that denominator is now a difference of 2 squares. And 1 minus cos squared, we can use a Pythagorean identity, replace it with sine squared, and cancel out 1 power of sine to leave behind this. So we did part B as well. And part B, remember, explicitly said show this equals that. So you know exactly when you're done because we started from one and got to the other. So now let's see exactly what was meant by simplify. So it said factor. Yep, that's what we did. We did a difference of 2 squares factoring in the numerator, and we factored a tangent out of the denominator. We canceled that out, and I guess that's where they wanted us to stop. Okay, fine. For part D, it was give it a common denominator. It said turn it into a single ratio. So what's the common denominator here? The common denominator is going to be sine u times cos u. So the first term has to get multiplied by cosine u over cosine u, and the second term has to get multiplied by sine u over sine u. This gives me 2 terms. The first one is cosine u plus sine u cos u over the denominator. The second one is cotangent u sine u minus cosine u sine u. When you multiply these out, these parentheses might make it more handy. Let me actually get my silly ovals out of the way. When you multiply this out, it might be clear now that you do in fact get a cosine plus sine u cos u and a cotan sine minus cosine sine, all over the same denominator now. Okay, is there anything you can do with this? Notice that we had a sine u cos u and a minus sine u cos u, so those can cancel out, leaving behind just cosine of u plus cotan u sine u over sine u cos u. Is this simplified compared to the original expression up here? I guess. I don't know. It's a little shorter to write. But we accomplished the goal. We made one ratio out of it. We made one fraction, which was all that was really asked. Okay, sure. Again, this part of the problem just said simplify. So now they're replacing cotangent with cosine over sine because, yeah, those sines are going to cancel out. Sorry, those sines are going to cancel out, leaving behind just a cosine in that second term. And then we just have 2 cos u over sine u cos u, and now notice that your cosines can cancel, giving just 2 over sine u, which I'm going to flip back, sorry, which you might rewrite as 2 cosecant u, depending. what you think is simpler. Some people would rather not have the fraction there. Other people would prefer to just have sines and cosines. Again, I totally avoid problems that just say simplify because it's not clear. Instead, we'll have problems like this. Establish this identity. Show the left is equal to the right. Okay? You don't start the problem by just writing this down and manipulating it because we don't know that it's true yet. So start with one side and transform it into the other. Now, generally, one side of the expression is going to be complicated and one side is going to be less complicated. So ask, would I rather take something complicated and change it into something simple, or would I start with the simple side and try to change it into the complicated one? You almost always want to start with the complicated side. It's much easier to simplify something because it's clear what you want to do. Compared to taking something simple and making it more complicated, there's way more options. There's lots of ways to make something worse, but there are relatively few ways to make it better. So simplifying something, it's usually more obvious what to do, whereas complicating something, it's less clear. So look at cosecant times tangent as one side and look at secant. Which side is more complicated? I'd say the left. It's got two things in it. So we start with the left-hand side, cosecant times tangent, and I want it to turn into just secant. But I have no idea how to get there yet. A really good first place is to just change everything to sines and cosines, because then you have less weird functions floating around and maybe things will become clearer. Cosecant is 1 over sine, tangent is 1 over cosine. Hey, those sines can cancel, leaving behind just 1 over cosine, which is secant. So now we know for a fact cosecant of theta times tangent of theta is always equal to secant of theta as long as both sides exist. Okay? And once you have transformed one side into the other, you know that you are done establishing an identity. Okay? There's no ambiguity about when you're actually done. So how about this? Sine squared minus theta plus cos squared minus theta equals 1. There are a couple of ways to do this. Let's see how the book does. Well, the left-hand side definitely looks more complicated. It's got negatives and trig functions and squares. Okay, we'll use even odd identities. So remember what sine squared means. It means take the sine and then square. And cos squared means take the cosine and then square. So they're just rewriting that exponent outside these parentheses to make it clearer. However, the sine of negative theta is negative sine theta, and the cosine of negative theta is cosine theta, because sine is odd and cosine is even, respectively. But a negative sine theta squared compared to a positive sine theta squared is the same thing, and now we just have sine squared theta plus cos squared theta equals 1, which is the Pythagorean identity. I would actually say there's an easier way to do this. So the Pythagorean identity says sine squared theta plus cos squared theta equals 1. Which theta is this true for? Anything. Sine squared of anything plus cosine squared of the same thing is equal to 1. Whether it has a minus sign in front of it or not, this was already just the Pythagorean identity. Sine squared of something plus cos squared of the same thing is always 1. Okay, so we're going to come back in a second video and go through several more examples of establishing these identities, and we're going to start with a nice checklist, sort of guidelines of how you should go through and do it. But rather than make one long video for this section, we're breaking it up into 2. So come on back for another video and we're going to work through more examples.